Okay, guys. So I'm going to go ahead and take us all the way through the 2018 and 2017 tests. So we'll have all of that on video just quickly at our disposal. With any luck, you'll be able to make good use of these videos as we head into the AP test coming up. So here we go. So first question, a student performs an experiment to determine the value of the enthalpy change, delta H reaction, for the oxidation reduction reaction represented by the balance equation above. Determine the oxidation number of chloride in NaOCl. Okay, so here's what's happening here. So O has to have a 2 minus or a -2 oxidation number, which means, and you know that sodium is going to be +1 because it doesn't really have it doesn't have another oxidation number. And so Cl is going to be +1 also, so that this chemical will have a balanced charge. Okay, so +1 for sodium, +1 for chloride, for chlorine, and then -2 for oxygen. And it's better to call that chlorine +1 than chloride because chloride is -1. So I apologize for the misuse of terminology. +1, there we are. Okay, so Cl +1, Na +1, and then O -2. All right, part B, calculate the number of grams of this guy needed to prepare 100 milliliters of 0.5 molar Na2S2O3. Okay, so first we need our molar mass of Na2S2O3. So what's that going to be? So sodium has a molar mass of 23 grams per mole. And then sulfur has a molar mass of 32. Draw better looking, 32 grams per mole. And then oxygen has a molar mass of 16 grams per mole. Okay, and the trick is we have 2 sodiums, we have 2 sulfurs, and we have 3 oxygens. So this is going to give us, I'm just going to write numbers here. So we're going to have 46, and then 64, and then you're going to have 48. Okay, so it's pretty easy to add 46 and 64. You're going to get 110 plus 48 is going to be 158. So you're ultimately going to wind up with 158 grams per mole. Okay, that's for this guy. All right, so Na2S2O3. Now we've got to figure out how many moles of this thing we actually have. So 100 milliliters at 0.5 molar is going to be 0.1 liters times, because 100 milliliters is 100 thousandths of a liter, so that means 0.1 liters, times 0.5 molar, which is 0.5 mole per liter, and our liters neatly cancel out, and we wind up with 0.05 moles. Okay, so we have 0.05 moles at this many grams per mole, right? So let's finish this off, and I'm going to go ahead and erase the board in about 3 seconds here. So 3, 2, 1. All right, so you have 0.05 times 158. Or sorry, let's get the units right. So 0.05 mole times 158 grams per mole equals, and our moles cancel out, 7.9 grams. Okay, 7.9 grams. There we go. And so that's the answer for part B. Okay, I'm going to erase the board in 3 seconds. So 3, 2, 1. All right, go with the red pen here, higher contrast. Okay, so I'm going to scroll down a little bit. And the question asks me, in the experiment, the student uses the solutions shown in the table below. So here are the solutions. Using, the balanced equation for the oxidation reduction reaction and the information in the table above, determine which reactant is the limiting reactant and justify your answer. Okay, so let's talk about this. So now I need to be scrolled up here. So let's talk about what we're dealing with here. So over here, we have 0.5 molar and 5 milliliters, right, for each of these guys. And if you want to do the math out, we're going to have the same amount of each, but let's go ahead and do that. So that many 0.5 moles per liter times 0.005 liters is going to give us for all situations here, we're going to wind up with for all of these, we're going to wind up with 2.5 times 10 to the negative third moles, or better yet, 2.5 millimole, okay, of each guy, of each one of these things. All right. So, so what does that mean? So you've got the same molar amount of each reactant, right? So then you got to ask yourself which reactant's going to get used up fastest. Well, if you take a look, we use 4 NaOCl for every 2 NaOH for every 1 Na2S2O3. So the NaOCl is going to get used up the fastest. Each time one reaction occurs, one complete reaction occurs, we use more copies of NaOCl or more formula units of NaOCl than we do formula units of any of these other ionic compounds. So that's how we know that the limiting reactant is going to be none other than NaOCl, okay? That is our limiting reactant, okay? NaOCl, and that's our rationale. Stoichiometrically, we use a 4 to 2 to 1 ratio of that guy to NaOH and Na2S2O3 respectively, okay? So let's take a look at the next question. Okay. This is a fun one. So all the solutions are originally at 20 degrees Celsius, and they're combined in an insulated calorimeter. The temperature of the reaction mixture is monitored as shown in the graph below. Okay, so according to the graph, what is the temperature change of the reaction mixture? All right, so we start at 20 degrees Celsius. So 20 degrees Celsius, and we wind up all the way over here at roughly 32.5 degrees Celsius, okay? So we wind up at 32.5 degrees Celsius. And so our delta T, our temperature change, equals 32.5. That's our final temperature. Sorry, 30 minus 20. And those are in degrees Celsius, of course, but I'm running out of real estate here. Equals 12.5 degrees Celsius. Okay, that's our delta T. That's part D. And then part E, the mass of the reaction mixture is 15.21 grams. Calculate the magnitude, and I'll scroll down a little bit, which is going to throw some of this other stuff off, but no, that's okay. Actually, that works. Okay, so calculate the magnitude of the heat energy in joules that is released during, yeah, that works still. Okay, during the reaction, assume that the specific heat of the reaction mixture is, that says 3.94 joules per gram degrees Celsius. So I will scroll down here. So 3.94 joules per gram degrees Celsius, and that the heat absorbed by the calorimeter is negligible. Okay, so let me erase these markings because we don't need them anymore. And here's what we've got. This is our specific heat, right? So this is this is a heat capacity question, or a specific heat capacity question, or a calorimetry question. So we use the equation Q, which is heat released, equals M C delta T, okay? And in that case, that equals the mass here. We have 15.21 grams, so 15.21 times specific heat, which is 3.94 joules per gram degrees Celsius. And this is, let's get the units there. So 15.21 grams times 3.94 joules gram degrees Celsius times finally 12.5 degrees Celsius. That's our delta T, and I'll draw a better looking one there. So 12.5 degrees Celsius. Okay, and then we see that the grams cancel out and the degrees Celsius cancel out. And what you wind up with is this number. So let me go ahead and punch in the calculation. So 15.21 times 3.94 times 12.5. Okay, 749. So we have 749 joules. Joules is the only unit that remains, okay? That's how many joules are left per reaction, okay? Per reaction. So 749 joules. Okay, and I'm gonna erase this for now. We'll bring some of these numbers back as necessary. And we've got, using the balanced equation for the oxidation reduction reaction and your answer to part C, calculate the value of the enthalpy change of the reaction in kilojoules per mole reaction. Okay, include the appropriate algebraic sign with your answer. Okay, so this reaction is losing 749 joules when what happens? When we react, as we said earlier, we reacted, how much did we react? We reacted we reacted, 2.5 times 10 to the negative third moles of this guy, okay? That's the, or sorry, not that guy, this guy. This is the only guy that reacts completely, okay? So we want per mole of reaction, right? So let's go ahead and do this in the conversion factor way. I like that the best. So we've got, okay, so that's part 2 here, and we're kind of low on screen real estate. Unfortunately, I can't share a whiteboard easily. So, okay, so here's what we've got going on. We've got a question that's asking for kilojoules per mole, right? So we start out with this 0.749 kilojoules per 0.0025 mole of NaOCl, okay, times 4 mole NaOCl per reaction. Okay, the AP, the College Board would say mole reaction, but I just don't feel comfortable thinking of it that way. So I'm going to say per reaction, and that's going to give you your answer. So your moles of NaOCl cancel out, and you're just going to wind up with kilojoules per reaction. And so when you do that, what do you get? You get that guy divided by 0.0025, and then that's going to equal this guy. We're going to multiply times 4. And so that's going to be roughly 1.2 times, okay, and I did, so 1.2 times, 1.2 times 10 to the third kilojoules. Come on. Turn on stylus. There we go. So 1.2 times 10 to the third kilojoules. Okay. 1.2 times 10 to the third kilojoules. Yep, that's correct. All right. So, in fact, I'm actually gonna, I want to double check to make sure that's fully correct. Let's go here. So this guy, joules, oh, reload. Aha, there we go. Yep, 1.2 times 10 to the third kilojoules. Okay, and per reaction. Okay, or per mole reaction. That's fine. All right, so let's open this test back up and continue on. Okay, here we go. Oh, this is a fun little question. All right, so let me blow this guy up. And I think I'm just going to do the 2018 test here on this video. I might change a couple things before we move on to the next, the 2017 test. So, okay, so a student investigates the reactions of nitrogen oxides. One of the reactions in the investigation requires an equal molar mixture of NO and NO2 gas. So here's the original reaction, and it asks, okay, equal molar mixtures of the two gases. Okay, okay. Which the student produces by using the reaction represented above. Okay, so I see. So we want to use, so the student is using this reaction to produce this. Okay, great. So that the student can later do this. Okay, so the particle level representation of the equal molar mixture of NO gas and NO2 gas in the flask at the completion of the reaction between NO and O2 is shown below in the box on the right. In the box below on the left, draw the particle level representation of the reactant mixture of the NO gas and O2 gas that would yield the product mixture shown in the box on the right. In your drawing, represent oxygen atoms and nitrogen atoms as indicated below. Okay, so basically every nitrogen that's shown on the right is going to be part of an NO molecule. So let's get that handled first. Let's figure out what's going on there. So how many nitrogens do we have? Well, 1, 2, 3, 4, 5, 6, 7, 8 nitrogen molecules. Or sorry, 8 nitrogen atoms. Every nitrogen atom is going to be part of an NO molecule on every nitrogen atom on the right is going to be part of an NO molecule on the left. Okay, so I've got 8 nitrogen atoms, and you'll notice, right, that we actually have 1, 2, 3, 4 NO molecules that never reacted with O2. So, okay, so what's going on? So we should have 8 of these NO molecules on the left. So you should have 8 times this little guy, N, O. Okay, you should have 8 of those. So 8 of those fellows. And then what about O2s? Well, let's count the total number of oxygens on the right side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 oxygens. So we've got 8 of them here. That means we have to have 2 O2 molecules. Okay, so 2 times O2, which is represented this way. All right, so that's what it should look like on the left. And I guess on the AP test, if you're writing on paper, you'd be expected to draw 8 of those things out, or maybe not. Like the College Board might be cool with you just labeling them that way. I'm not sure. I'd say read the solutions guide on that particular note. Okay, so the student reads in a reference text that NO and NO2 will react as represented by the equation below. Thermodynamic data for the reaction are given in the table below the equation. Great. Okay, so this one actually I won't do here because this has been a shortened AP curriculum and this material won't be covered on the test. So part B we're going to leave out, but part C we are going to do. So the student hypothesizes that increasing the temperature, so increasing the temperature will increase the amount of NO2 in the equilibrium mixture. Indicate whether you agree or disagree with the hypothesis and justify. Okay, so the important thing to notice here is that this is an exothermic reaction. So heat's being released, right? So you can think of heat as being a product. Now, if that's the case, temperature increasing is actually going to drive the equilibrium to the left. So the question asks, will this increase the amount of N2O3? Well, N2O3 is a product, so no. So we're going to disagree with this hypothesis, okay? Because according to Le Chatelier's principle, for an exothermic reaction, we should expect reactants to be favored as temperature is increased. All right, so next question. Or is this a continuation of this one? Oh, it's continuation, okay. So N2O3 reacts with water to form nitrous acid, HNO2 aqueous, a compound involved in the production of acid rain. The reaction is represented below. So N2O3 plus H2O yields 2HNO2 aqueous. Okay, so the skeletal structure of the HNO2 molecule is shown in the box below. Complete the Lewis electron dot diagram for HNO2, including any lone pair electrons. All right, so here's what's going to happen. Nitrogen needs to make 3 bonds, and so nitrogen's going to make 3 bonds. It's going to bond twice to this oxygen, okay, once to this oxygen, and it's going to have a lone pair. Now this oxygen on the right is going to have its own pair of lone pair electrons, and it's also going to have or it's going to have its own pair of lone pair. That's better. And then it's going to have yeah, that's it. It's going to have that double bond, and then this other oxygen on the left side, this guy is going to bond once to hydrogen and once to nitrogen. And so does that make sense? We have the right valence electron count. Let's just make sure, right? So we're going to have 1 from hydrogen, 6 from each. So hydrogen produces 1 valence electron. We have 2 times 6 from the oxygens, and we have 5 from the nitrogen. So if we add all these up, we get 13 plus 5 is 18. We should have 18 valence electrons. And do we? Let's count. So starting from the right, 2, 4, 6, 8, 10, 12, 14. Aha, I missed 2. 16, 18. See, that's why we always have to do this. I've done a gazillion of these Lewis structures, and even I goof up every now and again. So because we were supposed to show all of our lone pair electrons, we have to show those 2 lone pair that oxygen on the left side has. Okay, so my good technique saved me. And are all of our octets satisfied? So this oxygen on the right has access to 8 valence electrons, so does the nitrogen, so does the next oxygen, and the hydrogen has access to 2 valence electrons. That's a happy Lewis structure. Now the next question asks about the hybridization of the nitrogen atom. Okay, so look, this guy's got 1 lone pair, and then it's got 1 single bond, and then it's got 1 double bond. That's just classic sp2 hybridization. Okay, if you were to look at the reference frame of that nitrogen atom, you'd see a trigonal planar bond geometry. Okay, or sorry, electronic geometry is what you would see. All right, so that's sp2 hybridized for sure. So I'm going to go ahead and erase the board, and we're going to move on. All right, so next order of business. To produce an aqueous solution of HNO2, the student bubbles into O3 gas into distilled water. Assume that the reaction goes to completion and that the HNO2 is the only species produced. Okay, do we have a reaction for this? We do. Okay, that's the reaction right there. So that thing plus 1 molecule of water yields 2 HNO2 aqueous. Great. All right, so to determine the concentration of the acid, the resulting solution, the student titrates a 100 milliliter sample of the solution with 0.1 molar potassium hydroxide, which is a strong base. The neutralization reaction is represented below. The following titration curve shows the change in pH of the solution during the titration. Okay, so one thing you have to remember here is that this guy, I want to get his name right, nitrous acid is a strong acid. Okay, so nitrous acid is a strong acid, and so our equivalence point is going to be roughly right at a pH of 7 here. Okay, so it's almost, yeah, it's almost right at a pH of 7. Let's see what the Ka of HNO2 is. I'm not sure. I want to say it's a strong acid, but let's just double check. So, all right, so HNO2 Ka. Whoop. Ka. What is that guy? Oh no, he's a weak acid. Well, he's not a he's a fairly strong weak acid. So what is this guy? Ka. Golly, where is this guy? Yeah, 4.5 times 10 to the negative 4. Okay, so it's not a strong acid. I'm sorry, it's a weak acid. All right. See, good thing I checked. You got to check when you don't know. Okay, and I don't have to have these things memorized. So that's a weak acid. Not a terribly weak acid, but weak nonetheless. Okay, so there's a titration curve, and there's the pH change. Okay, great. All right, so use the titration curve in the information above to determine the initial concentration and estimate the pKa. Okay, so we kind of cheated on that one, but let's go ahead and use the information that we have to figure this out. So the initial concentration and the pKa. All right, so let's figure this one out. So the initial concentration. So, well, the pKa is going to happen. You're going to the pKa is equal to the pH at at 1/2 the neutralizing volume. So we can tell that the neutralizing volume is essentially 20 milliliters here. So 1/2 that volume is 10. So we actually know immediately, and this can be derived from the Henderson-Hasselbalch equation. We know that. The pKa is going to be roughly like 3.2. Okay, pKa is going to be roughly 3.2. But let's go ahead and play ball here. So what did we deal with? So we added 20 milliliters of 0.1 molar potassium hydroxide. So, whoops. So if you think about that, you've got 20 milliliters times 0.1 mole per 1,000 milliliters equals 2 divided by 1,000. We get rid of the milliliters, so 2 moles divided by 1,000, which equals 1/500th of a mole. Let's express that as a decimal. So 1/500 is going to be 2 thousandths, okay, which equals 2 times 10 to the negative third mole, okay, or 2 millimole. So we've got 2 millimole of potassium hydroxide that we're adding to neutralize the HNO2. So we started with 2 millimoles of HNO2. Okay, so we had 2 millimoles of HNO2 per 100 milliliter sample. So 2 times 10 to the negative third mole divided by 0.1 liter equals 2 times 10 to the negative second molar, okay, which equals 0.02 molar. So that's the molarity of our nitrous acid, okay, 0.02 molar. Is that what the question was asking? Yeah, it was. Good. Okay. So determine the initial concentration for HNO2 aqueous in the solution, and then find the pKa for HNO2. Okay. So for this one, we need our Henderson-Hasselbalch equation, I believe. So let me just go up and think about this. We got it from the graph, but let's go ahead and just work this out. So, okay. So here are our pH equations. So pH equals pKa plus log A minus over concentration of HA. And then pKa equals negative log of Ka. And then, okay, so negative log of Ka is your pKa, right? So what's the best way to solve this in terms of like what the College Board would want is my question. Yes. Okay. So you've got, and they don't give you they give you a starting pH, but they don't give you a Ka value, right? So you don't start with a Ka value, but you do start with a pH value in the initial part. Okay, so I think probably the simplest way to do this is actually just give it a straight equilibrium treatment. So I think we already went through it the other way with the Henderson-Hasselbalch actually. So using our graph. So here's what we can do. We can say that the initial pH, let's see if they give us a starting pH. They don't give us a starting pH number. Okay, so we'll estimate that starting pH at 2.5. So pH here, we'll call that pH equals 2.5. Okay, let's just say that's pH equals 2.5, right? Okay, so what does that allow us to do? That allows us to set up an equilibrium equations. So you know Ka equals concentration of H plus times the concentration of H in O minus all over the concentration of H, sorry, not HNO, but it's NO minus. It's Jake, I botched that. Okay, so NO2 minus, okay, all over HNO, NO2 concentration. Okay, so if our pH is 2.5, our H plus concentration is 10 to the negative 2.5. And we should expect the same for our concentration of NO2 minus, 10 to the negative 2.5. And then because that's such a small concentration, we should go ahead and expect our concentration of HNO2 to be roughly uh, 0.025 molar, but let's just go ahead and make it right. So 0.025 minus, okay, 10 to the power of negative 2.5. All right, and so that's our bottom part there, and that should give us our Ka that we just looked up for HNO2. So let's see if that actually happens. So we start out with okay, so 10 to the power of negative 2.5. No. Okay, and then what we're going to do is we're going to square that thing. And then, yeah, and that's obvious, right? 10 to the negative 2.5 squared is 10 to the negative 5. That makes sense. And we're going to divide all that by the quantity 0.025 minus 10 to the power of negative 2.5. Okay, and so that gives us 0.02, and let's go ahead and knock that out. Yeah, so I get 4.6 times 10 to the negative fourth, and let's see, we've got HNO2, HNO2 Ka. I just searched for it. Thanks for coming back up. And is that what we got? Yeah, 4.5 times 10 to the negative fourth. That's right. Okay, we did a great job. All right, so that's correct. Okay, so that's going to give us the right answer. And then let's go back over to our test. Okay, and so that's the end of that business. Let's go ahead and move on. Oh, it's one of the pKa. So Ka, so pKa is going to be the negative log of that thing. So why is this not erasing? Oh, turn on the stylus. Okay, so if Ka equals 4.6 times 10 to the negative fourth, then pKa equals negative log of 4.6 times 10 to the negative fourth. Okay, let's see what that gives us. So we're going to do, that's going to be roughly 3.4. Okay. 3.4 is what we're going to get there. All right, I'll clear this out and we can move on. F. During the titration, after a volume of 15 milliliters of 0.1 molar potassium hydroxide has been added, which species HNO2 or NO2 minus is present at a higher concentration in the solution? Justify your answer. Okay. During the titration after a volume of 15 milliliters, okay, if this stuff has been added, HNO2 or NO2 minus. Okay, so because we're on this side of the halfway point of the titration, so this is when we have equal amounts of NO2 minus and HNO2, because we're all the way over here at this point, okay, we actually have more NO2 minus, all right? Most of the acid has been neutralized, okay? Because our equivalence point happens right over here at 20 milliliters. So most of this guy, the HNO, the acid, has been neutralized at that point and converted to NO2 minus, right? And so what does that look like? We can look at our reaction above, right? So at that time, or at that point, we've added 15 milliliters. Most of this guy has been neutralized and turned into this guy, okay? So 3/4 have been turned into NO2 minus. Okay, so I don't know why, there we go. All right, great. So now we're gonna move on. We're gonna take a look at question number 3. So answer the following questions related to iron and its ions Fe2 plus and Fe3 plus. Okay, so, okay, so, okay, yeah, this guy's picking up my voice. It's just really strange. Okay. Okay, so here we go. Write the ground state electron configuration for the Fe2 plus ion. Okay, all right, well, that's easy. So let's look at our periodic table. So iron's over here is going to be Fe2 plus. Oh, this might be a special case. Golly, that's kind of a bummer. Okay, so I don't know if they want you to know that this is a special case or not. Let's take a look at it though. So this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s. Normally you go 4s2 and then 3d4, but a lot of times things that would go 3d4 actually like to be 3d5. So it might be 4s1, 3d5. Let's go ahead and check what the solutions say. So is that a special case? I don't know off the top of my head. Oh, that's interesting. So they don't do it that way. They just call it 3d6. That's interesting. Huh. That is a special case indeed because there's no 4s. Okay. And that's really interesting. I'm not sure about that one. I'm kind of surprised that's shown on the AP test. That's a toughie. I don't recall that one. Okay. Let's move on. So, all right. So the radii of the ions are given in the table above. Using principles of atomic structure, explain why the radius of Fe2 plus is larger than the radius of Fe3 plus. Okay, because you've removed an additional valence electron. So the electrons that remain are held even more tightly by the nucleus. This, yeah, that's that. They're just held even more tightly by the nucleus because there are fewer electrons relative to the number of protons. And then Fe3 plus ions interact more strongly with water molecules in aqueous solution than Fe2 plus ions do. Give one reason for this stronger interaction. Justify your answer using Coulomb's law. Okay, so in that case, you got a stronger charge, Fe3 plus, and so Coulomb's law says that opposite charges attract each other. So water has partially negative oxygen atoms because it's a polar molecule, and so those O atoms with a partial negative charge are going to be attracted more strongly to a more positively charged ion, Fe3 plus, versus the less positively charged Fe2 plus. And then a student obtains a solution that contains an unknown concentration of iron 2 plus aqueous. To determine the concentration of iron 2 plus in solution, the student titrates a sample of the solution with permanganate, um, which converts Fe2 plus to Fe3 plus, as represented by the following equation. Okay, write a balanced equation for the half reaction of the oxidation of Fe2 plus to Fe3 plus. Okay, so the half reaction. Okay, so I don't know if we're going to see this, but we might. So this is just Fe2 plus goes to Fe3 plus plus electron. Okay, so that's what a half reaction looks like. And this lets me know that I need to do a better job of covering electrochemistry. Okay, so that's that half reaction. And then the student titrates a 10 milliliter sample of Fe2 plus aqueous, calculate the value of Fe2 plus in the solution if it takes 17.48 milliliters of added 0.0350 molar permanganate to reach the equivalence point of the titration. Okay, so I see. So calculate the value, the concentration in the solution if this much of this is required. Okay, great. So you just calculate your number of moles here. So this many milliliters times this molarity. So you get 0.01748 liters times 0.035 mole per liter is going to give you a number of moles. And so let's go ahead and do the math. So 0.0174 times, or sorry, 0.0178, 0.01748 times 0.035 equals, yowzer, okay, 6.12 times 10 to the negative fourth moles. So 6.12 times 10 to the negative fourth mole. Okay, so that's how many you start with. And then you divide that number by 0.01 liters. So 0.01 is going to give you so that's going to give you 6.12 times 10 to the negative second, not liters, then to the negative second molar. Okay, that's your initial concentration of Fe2 plus. Let's go ahead and double check that answer. Those are ugly numbers. So I'm going to clear this. So what does this give us? There's Coulomb's law. Okay. So there's the half reaction, good. And then oh, did I not take into consideration some doggone? Okay, I didn't take the stoichiometry into consideration. That's on me. So you have to look that there are 5 of these things. So you take that value that I came up with and you multiply by 5. So there are 5 moles of iron 2 per 1 mole of permanganate. That's right. I should have looked at the thing. Okay, so there are actually 5 moles of that guy. So what did we do here of that guy to reach the equivalence point of the titration? Wait a tick. Hold up. This is part D. No, sorry, part E. So part E. That's exactly what we got for the molarity of the permanganate. Mole of that. I see. Yes, and that's true. Yes, you multiply. Yeah, that's a funky stoichiometric ratio. Okay, I'm not used to that. All right, so that's where I goofed up. So yeah, you got to multiply that by 5. So if you multiply our number times 5, so we wound up with 6.12 times 10 to the negative second molar. That's actually wrong because you actually titrate. So this doesn't happen for acid base titrations, but it happens like, yeah, it just doesn't happen, but it happens here. You get 5 moles of iron 2 plus titrated for every 1 mole of permanganate. So you have to actually multiply that value by 5. So if you multiply that by 5, you get 0.306 molar. Okay, and that's actually your answer. So we just goofed that up, and I'll show the answer again. So that's why I looked at this thing. You got to do that little step in the middle, which I forgot. Okay, so that gets you your correct answer. My apologies for the confusion. Now let's take a look at this next beast. Okay, so to deliver the 10 milliliter sample of iron 2, the solution in part E, the student has the choice of using one of the pieces of glassware listed below. A 25 milliliter burette, a 25 milliliter graduated cylinder, a 25 milliliter beaker, and a 25 milliliter volumetric flask. Explain why the 25 milliliter volumetric flask would be a poor choice for use delivering the required amount. Yeah, it'd be a poor choice because you just got to know what a volumetric flask looks like. So it's like this, and then shapes like this, and it's kind of flat on the bottom. It's got a little line here to tell you where the volume is. It'd be a terrible choice because it's only good for dispensing exactly this much. Okay, anything else would have gradations that would allow you to have a better idea of how much you'd added to get closer to 10 milliliters. Okay, and the best choice, of course, would be the burette. And that's a rough AP question. Okay, in a separate experiment, the student is given a sample of powdered iron solid that contains an inert impurity. The student uses a procedure to oxidize the iron solid in the sample to, that's going to be iron 3 oxide solid. The student collects the following data during the experiment. Okay, so mass of iron produced. Calculate the number of moles of iron in the Fe2 O3 produced. Okay, so that's straightforward, right? Because you know that this is pure. Okay, so if that's pure and we have this many grams of it, at least that's the assumption that I'm making. If that's the assumption I'm making. So if you assume that that's pure, then you have that many grams of it. So you do 7.531 grams times iron is, what's iron? Iron is number 26, so it's 56. Okay, so 56 grams per mole, or 58 point, yeah, 55.8 grams per mole, but I'm gonna call it 56 grams per mole. So that means that this guy is gonna have a mass of 56 times 2 plus 48. So 56 times 2 is going to be 112 plus 48 is going to give us 160. So 160 grams per mole. Or sorry, that's not the right way to do that. You want to do 1 mole per 160 grams. Grams cancel out. And that's going to give us, it's not a pretty number. So 7.5 divided by 160 equals 4.7 times 10 to the negative second moles. Okay, that's how many moles we get. So, okay, so that's how many moles we get. There we go. And let's just double check because heaven forbid I goof that up. Okay. So, yeah, 4.7 times 10 to the negative second moles. Okay, that's great. And then calculate the percent by mass of iron in the original sample of powdered Fe with the inert impurity. Okay, so you started out with let's see what that was again, 4.7 was it? Times 10 to the negative second, yeah. So you start out with 4.7 times 10 to the negative second mole, okay? The percent by mass of iron in the original sample of powdered iron solid with the inert impurity. Okay, so this is how many moles of, oh, I see, I'm sorry. So doggone it, this question is so, okay, we had actually that many moles of Fe, and you multiply that by 2. So that's not the number of moles of iron. So you multiply that by 2. So you get 9.4 times 10 to the negative second moles of Fe. Okay, so that's what you actually have. So you have 9.4 times 10 to the negative second moles of iron. Okay, and then we want the percent mass of iron, percent by mass of iron in the original sample. Okay, original sample, so that's this guy, right? So if you have that many moles of iron, what's your percent mass there? So you've got to go with 9.4 times 10 to the negative second moles of iron times 56 grams per mole of iron. And that's going to give you 5.3 roughly grams of iron. Okay, and then you have that per 6.724 grams, so divided by 6.724 is going to give us roughly 78%. Okay, so that many grams of iron, so 5.3 grams divided by 6.724 grams equals roughly 78%. Okay, so 78% by mass of iron. And I'm gonna double check. Yeah, that's good. Okay, and so that's that. And then part I here. So if the oxidation of iron solid in the original sample was incomplete so that some of the 7.531 gram of product was iron oxide instead of iron 2 oxide, so that's, sorry, iron 2 oxide instead of iron 3 oxide, would the calculated mass percent of Fe solid or iron solid in the original sample be higher or lower or the same as the actual mass percent of iron solid? Okay, man, this is one of those you got to wrap your head around. So the oxidation of the iron solid in the original sample was incomplete. What original solid? Original sample? Like, you must be talking about, okay, this thing. So this thing was incomplete. The oxidation of this was incomplete. So that some of this product was actually this instead of this. Would the calculated mass percent of the iron in the original sample be actually higher, lower, is the same as the actual mass percent of iron solid? Man, that's ugly. Okay, so what I'm being told here is that some of this, okay, is actually this instead of this. And in that case, what we have is 56 to 16 as our ratio of mass of iron to oxygen versus 112 to 48. Okay, so basically one of these to one of these versus two of these to three of these. So you're actually going to have a higher percentage iron in this stuff than you do in this stuff. So what in the world does that mean? So we've actually got so if this is true, we've actually got a lower percentage oxygen there than we think we do. So what that means is that we've got, in reality, a higher percentage of iron than we think we do. Okay, so a higher percentage of iron and a lower percentage of oxygen than we think we do. So that means that our percent mass, okay, is lower than it's supposed to be. So that means that this thing is actually purer than we think it is. So the amount of iron in the original sample is actually higher than the mass percent, or sorry, no, the calculated mass percent, of iron in the original sample is actually lower than the actual mass percent, because we thought there was more oxygen here than there actually was. Okay, hence we got fewer grams of iron than we actually should have gotten. Okay, man, that is a little brutal. Okay, so the calculated would be lower than the actual. A sample that contains, yeah, okay, I think I went through that, but the full, AP explanation is right there. Good job. Okay, glad we got that right. All right, are we almost done with this thing? Sweet mother of mercy. No, we got 4 pages to go. Oh, grief. Okay, it's 11 o'clock. How long has this taken me? Golly, I've got a degree in chemistry. I'm still doing this thing? How long have I been doing this? Oh, man. Okay, yikes. Okay, so the table above gives, how long do you have to do this, right? How long are you supposed to get to do one of these things? Grief. The table above gives the molecular structures and boiling points for the compound. Okay, the one thing, if I'm explaining all of this out, I'd probably do it faster if I were just solving the problems and hustling, but sweet mercy. The table above gives the molecular structures and boiling points for the compounds CS2, so carbon disulfide, and COS, okay? Great. In terms of the types and relative strengths of all the intermolecular forces in each compound, explain why the boiling point of CS2 is higher than that of COS. Okay, so here's the scoop. So neither of these is going to be a polar compound, okay? Because you got the carbon in the middle and you got two things that are more electronegative, pulling electrons in opposite directions. So because of that, there's really no net molecular dipole in either molecule. But these sulfur atoms are larger than the oxygen atom. Okay, that's a smaller atom, and therefore the sulfur atoms are more highly polarizable. So you're going to have higher van der Waals attractions among CS2 molecules than you will have among COS molecules. Okay, and so that's what's going on. You've got larger atoms for sulfur than you have for carbon, or sorry, not for carbon, well, for carbon, but really for oxygen. Is that's what changes? So you're going to have greater van der Waals interactions among the CS2 molecules. And so part B, a 10-gram sample of CS2 liquid is put in an evacuated 5.0 liter rigid container. The container is sealed and heated to 325 Kelvin, at which temperature all of the CS2 liquid is vaporized. Great. What is the pressure once all of it has vaporized? This PV equals nRT, but you got to calculate the number of moles here. So CS2, you've got carbon is 12 and you got sulfur is 32, but you got two of them. So, okay, so you got 64 plus 12, which is 76. So you got 76 grams per mole. And so you've got 10-gram sample. So you've got 76 grams times 1 mole per, or sorry, doggone it. You've got 10 grams times 1 mole per 76 grams, which is, it's going to be roughly equal to like 1.4 or 0.14 moles. Let's do it out. So 10 divided by 76 equals, yeah, okay, 1.3 or 0.13. Okay, so 0.13 moles of CS2. Okay, that's what you got. And you're at 325K in a 5 liter. So this is just PV equals nRT. And so what does it want? Pressure. Okay, so P equals nRT divided by V, which equals 0.13 times, we're going to use, let's just use liter atmospheres per mole Kelvin. So I think that's 0.080. So let's find R liter, can't get to the A, atmospheres. R, yeah, per mole Kelvin, doggone it, per mole Kelvin. So you get 0.082. Okay, great. 0.082. So you multiply that by 0.082 times the temperature, 325, all over 5 liters. Okay, so, I mean, let's just do this out. So that times 0.082 times 325, all divided by 5, equals 0.7. I get 0.7 atmospheres. Okay, 0.7 atmospheres. And what is that? AT, TM, I can't remember what that unit looks like. That's brutal. No, it is lowercase ATM. Good. Okay, it makes me feel happy. All right, so good. And then let's go ahead and see if that's the right answer. Golly, I hope it is. London dispersion or stronger. Yeah, okay, they call it dipole. Okay, that's fine, I guess. It's mostly going to be London dispersion. I don't think that's a strong dipole. And then you got 0.7. Okay, great. All right, cool. Okay, let's go back over here. So, oh man, I took it easy on us. Is this the last problem? Oh, this is so brutal. How long has this taken me? We gotta do like a timer at the end of this thing and see how long this was, because this is just brutal. Okay, so the ionization of HF, aqueous in water, is represented by the equation above. In a 0.035 molar HF aqueous solution, the percent ionization of HF is 13%. Okay, great. All right. So the two particulate representations of the ionization of HF molecules are shown below. Figure 1 and Figure 2, water molecules are not shown. Explain why the representation of ionization of HF molecules in water in Figure 1 is more accurate than the representation in Figure 2. Okay, so H3O plus HF. All right, so yeah, I mean, that's what you want to see, right? It's 13%. So roughly one in like every 7 or so molecules is ionized. So you got 1, 2, 3, 4, 5, 6, 7. Then the eighth one is not, right? And then one in every 8 is a better estimate. Yeah. So 1 in 8 is ionized. That makes good sense. Versus holy smacks, like everything's ionized on the right side. This is brutal. Like this is obviously correct. This is like 100% ionization over here. This is junk, right? Whereas this is roughly 13% ionization. That's correct. That's just a joke. That question is a joke. All right. So use the percent ionization to calculate Ka. Yeah, that's not a problem. Okay. So you don't really care, right? So it's 13% ionized. So really, whatever the starting concentration is, you're going to have 0.13 times 0.13. Okay. Like let's say you start with 1 molar, right? 1 molar HF, you're going to have 13% ionization. So 13% of it. So you're going to go 0.13 times 0. Over 0.87. So 0.13 squared divided by 0.87. So clear, you're going to have 0.13 times 0.13 divided by 0.87. That's going to be 1.2. So you get 1.2 times 10 to the negative second. Okay, that's what I get. Let's double check that. The first one's a joke. The second one. Okay, how did I? Oh, because doggone it, because I didn't take the initial concentration into consideration. Okay, I knew I was off somewhere. Okay, great. So you got to fix that. Okay, good. So I goofed up. Okay, so here we go. We got to start with these things, right? So 13% ionization of that guy, and what was the initial concentration? That's what I missed. See, that's the thing, when you like do this thing digitally, it's a little brutal because you can't see the whole page. So you start out with that much. Okay, so 0.035 molar HF, and that's what goes to 13%. So okay, so 0.035, so 0.035 times 0.13, that's going to give me 0.0455. So you're going to have 0.4, sorry, you're going to have 0.00455 squared divided by, it's going to be 0.035 minus 0.04, sorry, 0.00455. Okay, that's 0.03045. Okay, so then you got to actually do this out. So 0.00455 times 0.00455 divided by 0.03045. Okay, and that gives us 6.8 times 10 to the negative fourth. Okay, tell me that's right. Yes, 6.8 times 10 to the negative fourth. Okay, that's good. All right. Okay, and then the AP answers have a nice rice table, so I don't, I'm not gonna, I don't have really board real estate to write one of those here. Okay, so that's correct. And then if 50 milliliters of distilled water are added to 50 milliliters of 0.035 molar HF, will the percent ionization of HF aqueous in the solution increase, decrease, or remain the same? Justify your answer with an explanation. Okay. So basically, Ka is a constant, right? So Ka equals concentration of H plus times concentration of F minus all over concentration of HF, right? And so what you're doing in this case is you're diluting everything by half. So essentially what you're doing is you could just do the calculation. That might be the easiest thing, right? So now that you know your Ka is 6.8 times 10 to the negative fourth, okay? That's going to be equal to 0.035. You're going to divide that by 2. So it's going to be 0.0175, okay? And that's your denominator. So it's going to be 0.0175 minus x divided by x squared, and you go ahead and solve for x. And when you do that, what you'll find is that your percent ionization has actually increased. Okay, so x divided by this guy is going to be greater than 13%. And you might have to ask yourself why, right? So what's happening here is that relative to your earlier concentrations, you've now got half. So if these were the original concentrations, you'd actually have 1/2 and 1/2 on the top here. So you'd multiply by a fourth throughout, or sorry, you'd multiply by a half throughout, which would give you a factor of 1/4. So your numerator would be getting disproportionately small relative to your denominator. So like here, look, so you have, instead of your original concentration, so like if this is original and original and original, right? You suddenly have 1/2 the original concentration times another 1/2 all over 1/2, right? So if there were no change in percent ionization, right, this would get multiplied through. Well, these two would cancel out, but then you'd have 1/2 of your Ka. That's no good. So these two have to grow in concentration or increase in concentration to relative to this guy in order to get rid of this factor over here. So your percent ionization is going to increase. And there are two different ways of doing that, right? There's the straight numerical way, which will get the job done. I would go with that, right? And then there's the like theoretical or conceptual method that would also do the trick. All right, so let's move on. Oh, okay, a galvanic cell. Okay. And then guys, if you see one of these on the test, just go ahead and let it go, because we really didn't talk about this. And this is a lot of like special, like I think a lot of this really gets to delta G, which is not covered on this year's AP test. Okay, so that's gone. Let's take a look at number 7 here. It looks like they were really pretty fond of these like binding energy questions. So relative number of electrons, binding energy. Okay, so complete the photoelectron spectrum of the complete photoelectron spectrum of an element is represented above. Identify the element. Okay, so number of electrons, binding energy. These are heavy. These are less bound. Okay, so what do we have here? So you know that your first peak is going to be 1s2. So 1s2, then you've got 2s2, and then you've got, it looks like you've got 3 electrons here, so 2p3. So 1s2, 2s2, 2p3. Okay, 2p3. So this guy has 5 valence electrons. Yeah, that's nitrogen. Okay, this is nitrogen. And a radioactive isotope decays with a half-life of 10 minutes. Woo! Calculate the rate constant for the radioactive decay. Include units with your answer. Okay, so I remember us doing all of this. Darn. So I wonder, I can't remember. I remember we had an equation for this thing, but I wonder if this is included in our equation sheet. So I remember these problems not being so bad. So half-life is 10 minutes. What's the rate constant? Let's see if they have like a decay. Half-life, aha, look at that. Okay, so the half-life is 0.693 over the rate constant. Okay, so that's 10 minutes. So we'll use 10. So 0.693, is that, let's double check that I memorized it. 0.693 over the rate constant, yeah. Okay, let's go back down. So you use this bad boy right here. So T of 1/2 equals 0.693 over the rate constant, and we can plug in. So you've got 10 minutes, right? So let's just go with 10 minutes, and the rate constant units with your answer. Okay, so it's going to be, so K equals 0.693. I'm just multiplying both sides by 10 minutes, and or so I'm dividing both sides by 10 minutes and multiplying both sides by K, divided by 10 minutes, which equals, okay, 0.0693 inverse minutes. Okay, that's your answer for part B. Let's just double check that that's correct. Nitrogen and this thing here, so skip this. Okay, so skip that. Nitrogen, yep, good, we got that right. Then let's go back to the next question and do this guy. 64 atoms of the radioactive isotope originally present in a sample. What is the expected amount of time that will pass until only 1 atom of the isotope remains? Oh, this is fun. Okay, so 64 equals 2 to the power of 6, right? So in order to get all the way down, we're going to have to, let's see how many half-lives it takes to actually get to 1. So 2 to the power of 6. So 2 to the first is 2. So we got to go so from 6 to 5, 4, 3, 2, 1, and then one more half-life gets you to 0. So yeah, 6. So we're going to have to go 6 half-lives to get down to 1. So 6 times 10. So 6 times 10 equals 60 minutes. Okay. The other thing that you could do is you could do log base 2 of 64, and that would give you 6 half-lives, right? That give you 6. Okay. If you need to do change of base, you do log base 10 of 64 divided by log base 10 of 2, and that should also equal 6. Okay. Let's just double check that that's correct. So I forget my change of base formula sometimes. So 64 log base 10 divided by 2 log base 10 equals 6. Yeah, that's correct. Good, good. Okay, so let's double check that that's correct. 60 minutes. Yes, sir. All right, and that, the scoop, it is. So we are done with this guy. That took unreasonably long. I mean, sweet mother of mercy. I don't know how long that took, but that took a long time. How many minutes do you get for this test? Grief. You get how many minutes? Originally, this is the original test. This is a full length test. So I got to ask myself how many minutes you're supposed to get for this thing. But get your constants here. Wow, 1 hour and 45 minutes. Man, it felt like it took me that long. Okay. And we skipped some of that stuff. Woo! All right. So that's it. Yeah, we're gonna look at this. This is just 2018 AP Chemistry Free Response test. That's all I've got time to go through tonight. Okay, so that's the video. Enjoy. Good luck. Please let me know if you have any questions or if you think that that I could have explained something better, or if you found an error or something. Okay. All right. Thank you.